Okay. So, as I said, it's a joint work. It's a long-time progress, a program which I start with Stiti, and it's still ongoing. In fact, with the influence of John. Hello, John. And another thing I want to talk about. So I move to the next slide. So the next slide, in the bottom, you see the Navier-Stokes equation, incompressible Navier-Stokes equation that everyone in this audience knows. And the point is that I look at a problem where the viscosity goes to zero, where the initial data is given, and when there is a no-slip boundary condition. And as you know, if there is no slip boundary condition, if you go to the Euler equation, only the tangential component, the normal component, will remain to zero. The tangential component will go from zero to non-zero value, and this will generate a boundary layer, as I said here on the slide. That's well known. In fact, this, I think, it was at the level of mathematics in my community. It was observed first by Prand, 904, and then the equation he proposed are called the Prand equation, of course, and they introduce a boundary layer, which is of the order of the square root of nu, the square root of, in the rescaling, it is the square root of the Reynolds number. Now, just from a mathematical point of view, I observe that this is, from my experience, what I know, the first boundary layer analysis that was proposed to the mathematical community, and it was the origin, this parabolic scaling, of many other problems, many in linear problems. But they turn out to be the most subtle one. And the reason why they were the most subtle one is that the nonlinearity is strong enough. Strong enough means that it may generate turbulence that from the singularity near the boundary, the singularity will propagate in the bulk of the fluid, and at the limit, for nu going to zero, the limit may be seriously different from the solution of the earlier equation. Now, how that's happened, this is a field of study, of course, and I will try to contribute modestly to this point. And what I observe is that the same people, Prand, with his former student von Karman, they suggest in the 1920s that the origin of such singular behavior, what's happened, not in the parabolic boundary layer, which is the size of square root of nu, but in the region which is the order of nu. Nu is much smaller than the square root of nu. Well, that's what we are. And in fact, in trying to tackle this problem from the mathematical point of view, the first milestone was the paper of Cato. Now it's extremely popular in our community. It appeared in 1984, and it's a paper where Cato does not prove the convergence to the Euler equation or the non-convergence, but he proves the relation between this convergence and the absence of anomalous energy dissipation in the boundary layer, and in the boundary layer, which is in agreement with the von Karman-Prand law, will be of the order of nu. So, Cato had a theorem for this equivalence, convergence to the Euler, and no no singularity in the region of order nu. Now, with Edwis-TT, we catch that, and we propose an avatar or several forms of this theorem of Cato, which is based on a very simple Grunwald estimate, I would say in the type weak-strong relation as used or introduced in our community, mostly by Dafermos. So I'll give the picture of the protagonist, Brand, von Karman, and Cato on the bottom, and I write the theorem that I wanted to say. It's a theorem which is valid in any dimension, so in physics, it will be in dimension 2 and 3. And it goes like that. You consider a solution of the Euler equation which is regular enough. Regular enough means that it is Lipschitz, that the gradient for some finite time from 0 to t is less than infinity. Consider a viscosity which is positive, a new solution of the Navier-Stokes. Now, after the construction of wild solution with the influence of this Laszlo and Camillo and others, we found it's clear now that to deal with physical solution, one has to leave to deal with Loray solution, which means that I have the energy dissipation valid for weak solution, which says that the solution at time t and dissipation from 0 to t is less than the energy of the solution at time 0, which is the equation 1. And then look at let nu going to 0. Then I assume that the reason it's a theorem of equivalence, that the vorticity, which is the curl of the velocity, satisfied a condition, which is the integral from 0 to t of the vorticity computed on the boundary. Take the scalar and multiply that, and 2D it's a scalar, otherwise you take the scalar product, multiply by the tangent component of the velocity, take this quantity which is in equation 2, assume that this quantity goes to 0. Now, with 1, there are weak limits, and the theorem we have, which is a version of the Cato theorem, is that if this limit goes to 0, that implies that that u nu of t will that the u nu of t will, or its weak limit will go to the solution of Euler, and you have a very precise estimate, exponential 2t time the gradient of u in L infinity, and you have the jump from the initial data u nu of 0 minus u0, which is the equation 3. That tells you exactly how you get the convergence under the hypothesis 2. Now, this hypothesis may be interesting to find an interpretation, because omega nu on the boundary for Navier-Stokes will be exactly the normal derivative of the tangent component of the velocity, which means that I have another equivalent condition, which is exactly that you look at a normal derivative of the tangent component, take the scalar product with the tangent velocity, integrate from 0 to t, and you just take the negative part, because it's enough for the limit, and you want this quantity to go to 0. Now, if I go to this very sketchy proof, I look at a detachment, what is known in physics, that if you have an airfold, for instance, and the air going around the airfold, there may be a detachment point, which is really very sketchy on my slide. And that means that in some region, which will be maybe bounded here, the velocity, instead of going all the way like that, detach from the boundary and make a turn. And this makes a turn, gives the bad sign for this quantity, which may make it not go to zero if it is large enough, this quantity, and in particular you multiply by nu, it has to be large enough so that this goes to zero. Now, when I first time I gave this talk, John was in the audience, and he told me that this is related to the vortex vortices, which mean that the vortices which is generated on the boundary may be large enough to violate this condition. If it doesn't violate it, it will go to the solution of the earlier equation. That's the point I want to elaborate on using the rest of the story. Okay, I move with it. And so that's basically the object of my talk. Now, if I move along, I want to give condition for which I can get a direct proof. I will do a direct proof of this relation with the minus nu time du nu over dn. Okay, now I want, and now by science, by experiment, one knows that this may not be in general the case. This may be this will be valid for short time, not for a long time, and under strong hypothesis. And the hypothesis is that you consider as initial data which are analytic, you consider a boundary which is analytic, that means very regular, and then you prove that for a positive time, which is independent of nu, you have the control of the velocity, which says that the square root of nu, of the Reynolds number, multiplied by the subnorm of the vorticity on the boundary is less than infinity. That's enough to get the equation 2. So this is the goal of the rest of my talk, to tell you how one can prove that, and how it is related, mildly related, to this question of curvature of the boundary. Okay, yes, you are with me. I can check, but I hope so. Okay, so there you make simple observation that what Leray, weak solution Leray, tells you that Leray solution takes you 5, that you integrate from 0 to infinity to t, omega nu in L2 of omega, this in interior, it's 5. This is less than a constant. Well, that's the a priori energy estimate. I want the same estimate, but just restrict to the boundary. So if something is L2, its value on the boundary may be singular, and that means that this is 6 is of the same nature, but it's much subtle than 5. And if I go back to the different type of version of the Cato theorem, you can make it in a duality argument and find out it is enough to have the vorticity on the same region on the boundary, small with respect to nu. In 7, I wrote L2, but any norm by duality will be okay if the solution of the target of the earlier equation is small enough. So that's the thing, I hope so. Now, this is the sharpest condition, but the fact, which is that the point I want to underline here, is that I cannot prove the convergence with a weaker estimate. The estimate I will have is of the order of square root of nu, which in fact is really related to the Brand scaling. And that's where the analyticity appears. And in fact, in the production of this paper, we found out also a paper of Wang and Wang in the fluid mechanics, where they have another type of similar type of result coming by using the Brand expansion. But of course, the analyticity is absolutely compulsory. Maybe some people can extend it to Gevrey, but very high regularity is definitely necessary. Okay, so that's the goal of the technical part of my talk, and it goes more or less to the story of the problem. So the issue is the control of the vorticity on the boundary. Now, it turns out that if you write the Navier-Stokes equation with zero vorticity, it will be natural to have a boundary condition on the vorticity. And this is something which was proposed already by Anderson in 2014 for numerical computation, and I will discuss this Maekawa boundary condition. It's something which will be very useful. I explain to you why it works, and it comes nicely in the problem. But as you will see in the next slide, this Maekawa condition, this Anderson condition, really relies on some type of analyticity. And then it was used by Maekawa to prove the convergence of the Navier-Stokes to the Euler on a very stringent hypothesis, which is that the initial data, the support of the vorticity does not touch the boundary, and it was done in the half space. So half space, initial data with vorticity away from the boundary, you get the convergence to the Euler. Now, after that, progress were made on this question. The first progress was a paper of Toan Nguyen and Truong Nguyen, and they proved the Maekawa result for analytic data in the half space, even if they touch the boundary. And then the question is whether or not it's really necessary for this type of short-time result that the initial data will be analytic everywhere. The analyticity away from the boundary has been relaxed in a paper of Vikol-Wang in 2020, Kukavika, Vikol, and Wang. Now, all that was done in the half space. Now, to do the point 4 is to move from the half space to the domain which has a curvature, or more or less into any kind of domain with analytic boundary. And for that, point 4 is to use a very sharp analysis of the regularity of the evolution of the fluid near the boundary. And it's something that I already worked out in 2022, just not for nu going to 0, but looking at the extension of the Onsager conjecture that everyone in the audience may know, the 1/3 Onsager regularity Onsager condition, and it needed that to show that the pressure on the boundary was also in the same regularity as the velocity. And this is not trivial, this is not always true. There's some extension of this result, and it was a paper that I did with Citi, and which we extend later on with Daniel Boutros for 3D. So that's the point. So I will go 1, 2, 3, 4, and that will be the end of my talk, if I finish that in time. Okay, so far so good. So what is Maekawa? Maekawa, you have the equation 10 on the boundary, which is in 2D with a very nice parabolic equation. It's a very nice parabolic equation, non-linear, but there's no more pressure. But then the boundary condition is at stake. Now, how you get the boundary condition? You just start with a potential phi for the to describe the velocity in terms of the vorticity. So that means taking the Laplacian and inverting the Laplacian with Dirichlet-Neumann boundary condition, which means that this potential phi is 0 on the, or it is constant on the boundary. If you do so, you just, when you take the verticity, you observe that they will tell you that that if you apply look at the vorticity, that will tell you that if you take the inverse of the Laplace omega, the curl of that, that will give you u, and you know that if u is the tangent u is 0 on the boundary, dt of u is also to 0, so you get this equation. And this equation is expressed as a formula 8, the normal derivative of the Dirichlet minus Laplacian minus 1 construct to apply to new Laplacian minus u nabla of omega. This thing should be equal to 0. Now, why it's gone? Yeah. Now, why that means that if you have Laplacian minus 1 Laplacian, you should try to, it looks like Laplacian minus 1 Laplacian, that will be the identity. Well, this is not true because the Laplacian of the vorticity on the boundary is not 0 multiplied by nu, so you cannot invert this thing naturally, but you can make omega equal to 0 on the boundary, provided you subtract to omega a quantity which is omega star, which is the solution of the Dirichlet problem with 0 inside, with on the boundary minus the n of omega, which will make this quantity the n of omega minus you take omega star. So if you subtract omega star here, the Laplacian of omega star 0, you introduce naturally what is called the Dirichlet-Neumann operator, with a change of sign respected to the mathematical community. So you get, by the equation 8, you get the equation which is the first equation for 10, which gives you a boundary condition for the problem. Well, bingo, you have an equation for the vorticity and an equation for the boundary condition. Very good, that makes our construction. Then, why don't you use that for in all cases for Navier-Stokes? The answer is that if you play with standard energy estimate, you multiply by omega nu, what you obtain what the lower type relation quantity on the left-hand side, and on the right-hand side, a thing which is bad. Bad because there is a 1 over nu here, that's bad for nu going to 0, For classical problems where you had all other type of boundary condition, it could be balanced by the first quantity, but when the no-slip boundary condition with the with the Anderson-Maekawa condition, this quantity has the wrong sign, so it doesn't help. So that means that this doesn't work. But it's clear that it is a problem with a boundary condition which is well posed in a domain with, this is well posed locally in time in the class of very smooth solution, because you can balance the bad behavior of the right-hand side by the, you can balance the bad behavior of the right-hand side by the good sign of the boundary effect when it's not the no-slip boundary condition, and then you can prove that it is well posed in the analytic setting. And this is the comment I made at the bottom is explain why this was introduced by Anderson. The reason is that if you make numerical computation for finite time, then you have a discretization, and you have an evolution equation which is dependent of time in finite dimension. It's always analytic, so it's nice for small data, for smooth data that will be approximated by analytic solutions, and very small Reynolds number, which was proposed by Maekawa. Okay, now then I have to change the boundary condition. So that's the Maekawa condition that I'm going to use. Now I need to flatten the boundary condition. And I really use the idea that in 2D, dimension 2, any open set by a conformal mapping can be transformed in another one by an analytic transformation which preserve the angles. So there is no wonder, which is the fact that I can make the boundary omega as a circle. It's the analytic curve becomes d omega, which is r over z L. L is the length of the fluid. So you have the tangent component. The tangent component is with prime. It is equal, by the parametrization, it is equal to 1. You can write the normal component, which is the orthogonal to this one. And with the normal component and the tangent component, you have the vertex, the curvature of the boundary condition. The curvature of the boundary condition is gamma of theta. It's equal to x1, second derivative of x1 minus x multiplied by x, the first derivative of x2 minus the first derivative of x1 multiplied by the second derivative of x2. And you have a very natural definition of the distance of x over omega, because if you are close enough, then you have only one point x over omega, which gives the distance from x to d omega. And the consequence is that you have an analytic description of the neighborhood of the boundary, which I call V delta. Will be maybe easier, and I will need one more thing. I will use the invariance of the parabolic equation, which is in equation 14, which is well known, which is that if you multiply lambda square t by lambda square, theta by lambda, and z by lambda, because they are scaling parameter, then you keep the Navier-Stokes equation, the parabolic equation, and if you do this transformation, that will change. This transformation will change the boundary in the equation 15, if you change it in the equation 15, you see that if you take lambda small enough, that will be enough to control the vorticity. So that, and then I just mentioned that in the rest of the proof, when this is obvious, no confusion, I will omit the title, the tilde, for the variable lambda squared t, lambda theta, lambda z. So then the rest is to adapt the computation of Gien and Gien to the case where you have changed the curvature into a flat boundary, but with a convenient parametrization. Okay, so to do that, since on the way beginning there was at the bottom of this boundary V delta, I have to focus on the boundary. To focus on the boundary, and I introduce two nice functions to localize. One is called phi b of x, b for boundary, it's equal to 1 near the boundary and equal to 0 away. And the other one is phi I of x is equal to 0 near the boundary and equal to 1 elsewhere. And I wrote, and this is not, I won't use that as a partition of unity, but I will just observe that by saying that it's equivalent, that the singularity of omega of nu is driven by the singularity of phi b omega of nu plus phi I of omega of nu. Because if phi I is good or phi b has to be controlled, it's phi b which gives the result, and vice versa. And also what is important is that near the boundary, I have phi b which is equal to 1, so there will be no modification on the Maekawa boundary condition. Now, it's to make the thing clearer, it's much natural, it will be natural to look at the picture and keep in mind this condition 16, but try to look at it on a picture. So here is the picture for the rest of my talk. On the bottom, I put the open set omega, and V delta is what is indicated in red here. And I just insist to the fact that this is local, so I could deal in the same way with a region where there are I will locate near this boundary and locate near this boundary and then 0 all the way. Now on this graph on the top, I had to put two different things, but they will be both important. So R of Z represent the distance from the boundary to the interior. R of Z represent the distance to the interior. So forget about that, these lines for 1 minute and the imaginary lines. So I have first function that localize away from the boundary, which is phi I. So if I multiply by phi I have a function for omega which goes like that, which means it doesn't touch the boundary. If it doesn't touch the boundary, I can use standard finite time estimates for the Navier-Stokes equation. I take derivative of 2 order 3, multiply by the third derivative of omega, integrate by part. Since there is no boundary effect, for a short time, you will have the convergence. The other one is this quantity, but this quantity, but then you have to evaluate how big is the interior solution in this region. Now you take the other one, which is a genuine solution near the boundary and goes to 0 here. So the one which is red here, and it goes to 0 inside. This is the one on which the Maekawa condition will be active, where all the analyticity will be active. So I will have to use analytic estimate. Analytic estimate can be represented by extending here on the imaginary axis and take the variable z, introduce an analytic expansion, and away from the boundary, look at lines on this type, region of this type, this broken curve, which are embedded one on the other, which lives in the analytic domain, and I will use L1 estimate of the vorticity on this boundary, one over the other. Obviously, when you have an estimate here, that give the control inside, and for analytic expansion, that will also give control of the non-linearity. So you can hope here to have a Cauchy-Kovalevsky or a Nash-Moser theorem in the spirit of Yen and Gen in the half-space. Now you combine these two things, and you hope to have estimate. And that's what I am going to explain in the rest of the talk. Okay. So first, I have in view the Anderson boundary condition, Anderson-Maekawa boundary condition, which I call this 17. And for this one, I have to study what is omega nu multiplied by a function which is equal to 1 near the boundary. So it will be an equation of that type with remainder term. Here is the remainder, which I wrote, which hopefully will be harmless, and the same thing for the Maekawa boundary condition, because on the boundary, phi b is equal to 1, so this is omega nu. So you have an equation for the parabolic inside with remainder, and for the equation with remainder. And this system, I called it 18. Okay, so I want to compute the 18. And for this, since it's near the boundary, I can, which is here, I can use the rescaled boundary condition, which I call the geodesic boundary condition, which I've introduced beforehand. So the first thing is to change the Laplacian. And if I change the Laplacian, since I want, it's clear that if we have an elliptic equation, if I make a change of coordinates, I will still have an elliptic equation. But I want more. I want this equation to be the perturbation of something which is exactly the half Laplacian on the half space, which is d2 of z squared plus d2 with respect to theta on the half space. Well, that goes well in principle. There are terms which are negligible, but there's a term that you cannot get rid immediately, which introduces the second derivative of the time, and which may not be balanced by the first one. So but then there is a coefficient here, and the coefficient is m of z theta, which has a negative sign, which is given in the second equation of 19. Now, just observe that I have the vorticity here, that I have the vorticity there, and that I have a lambda square. And if I have this, taking lambda small enough, that will kill this quantity which could be observed absorbed by the du over theta. And this is where appears the condition on the curvature of the boundary. So that's a summary of what is done. You have an half-space problem with a new lambda square, which multiplies something which is a coefficient which depends on the boundary. Then you have other terms which are less important, and you have same thing for the Maekawa boundary condition. And I put in red the thing I discussed today, which is the role of lambda is to flatten the curvature near the boundary condition. In the change of variable lambda theta, giving lambda theta, the curvature is changed in lambda cube gamma of lambda theta. This makes appear a coefficient lambda square in front of lambda square of m at theta, second derivative of omega, which can be dominated by the Laplacian. And once again, and that's the last time I will say it, this goes very well with the observation that the vorticity generated in the fluid is generated, it can be big when you have a big curved boundary, which correspond to the vortices, which I want to ignore or to consider as a small quantity in the present talk. Here I am. Now, for people which are used to extension to the complex domain, there is one slide to tell you that this boundary condition here, that there are nice relation between integration on this boundary condition line, the integration on the interior, and even the smaller one, as soon as you deal with analytic function, and if you use the Cauchy representation formula for analytic function. So that's the 21, which maybe just ask you to believe now, but which is very classical for people working with Nash-Moser theorem or Cauchy-Lipschitz theorem in the framework of analytic function. So just believe that they will be used below, and I move to the equation. So here is this picture that I will still keep in mind. And then I introduce a compound norm, which is made by the analytic norm of omega nu, which is evaluated in geodesic rescale variable, and the Sobolev, say, in H3 or of omega IE, which is the extension of R2 of the truncated solution, and which is done, all that is done for parameter delta rho 0 lambda small enough. And for that, you introduce a quantity which I will call the compound norm. First, I look at this quantity A beta lambda. It's the analytic norm on the previous slide of omega 1 beta, the omega 2 1 beta, and you have a weight which corresponds to the fact that you will shrink the analytic domain with time, make it smaller and smaller as time evolves to have a control that will be valid for finite time. So this is the analytic norm. Then there is what I call the compound norm. Compound norm is made with the analytic norm, which is defined in 22, plus the Sobolev norm, which is defined by the solution, but far away, say for the solution, or phi of omega, which is for delta 0/2 greater than 23. And then, with that, one has the estimate that this quantity is bounded by C0 in omega 2, 1 in the plus omega 0, 4, just what is given by 24, which is a nice quadratic estimate because you have the initial data, you have a coefficient, and you have this quantity square. And that tell you that will tell you that if this quantity, this one is given, but if this is, if the initial data C R, which I call the compound norm, is small enough, then over the time it's an x square minus less than x, it's an x of t less than a constant a plus a coefficient that multiplies x squared. And if you start from x of 0 small enough, just looking at this equation, that will tell you that this will remain for a finite time less than what is the initial data. So that's the estimate. Okay, now I will skip, so really going back to the picture, that means that the compound norm use that for the analyticity, that's for the exterior, and then it's combined because for all the solution, I use the information, the Sobolev estimate to estimate the red quantity here, and the analytic estimate to look at this region on the left. And maybe this analysis, between interaction near the boundary and slightly away from the boundary, may be used in further analysis of the generation of turbulence or vorticity away from the boundary. Now I don't know how much time I have, and I don't want to give you too much technique. I just gave some historical comment. The next thing is that first you deal with the half-space formula in the problem in the half-space, as it was done by the Thun-Gien, which I call Gien square. And what is nice is that the F-space for an equation like d omega over dt minus nu Laplacian of omega plus u nabla omega, you put u nabla omega on the right-hand side, and you can use the explicit representation of the solution with z, with theta being a parameter in the half space. You have quantity you can put in this equation, you have a reminder, you have very nice estimate, and this goes in the estimate. And then when you have that, you just compute the estimate, you bound the reminders. Once again, you have to see that the right-hand side will be absorbed if this lambda is small enough, using different type, and then you combine with the Sobolev estimate. I just move down, and then when you have done this estimate for the linearized equation, you can use all the rest on the boundary as a perturbation. And at this point, for the analytic solution near the boundary, that you use the classical Cauchy formula between the interpretation, the size of the bound of the solution in the domain and the size of the solution in the bigger domain with gain of derivative. And at the end of the day, you get the equation 32 for the control of u nabla of omega beta, which is the most nonlinear term in the boundary and which will appear at the boundary equation. Okay, and then you you just use the standard Sobolev estimates. For technical reasons, for the Sobolev, for all the problem, you have better to do that for the derivative, so that end up the computation of the compound norm. Well, I don't want you to check all the detail of the story that I told, but I wanted really to emphasize this picture. You have estimates which are classical here for this effect of this of the interior of the. This is computed by the boundary layer solution on the interior. So if you have the boundary layer solution, you have a classical estimate here, and on the other hand, here you have once again, here you have the boundary layer solution that will give you an estimate on the interior. So all this complicated estimate is just an interplay between some Sobolev information here and analytic information near the boundaries. And this has to be done in detail, but that makes the proof work and gives this theorem 23. Okay, can make just some small remark to finish. And there can make some conclusion, which I made in already whenever I start this program, and they come all the way. The fact that in general, we don't expect that the weak limit will be everywhere the solution of the Euler equation. I am just giving sufficient condition as much as I can to ensure that, but one supposes that this in general may not be the case. It's the agreement with with numerical computation. It's also in full agreement with what you see in nature. You see turbulence going away from the boundary in the wake. And if you just use the avatar, which I propose with Edris, the vorticity is the velocity on the boundary, the normal derivative of the velocity. If this quantity is not big, there will be no force on the boundary, and for instance, bird or plane will not fly. Now, and in fact, there are good reasons at the mathematical level why it will hold only for a short time. You need two things. You need first that the Prand equation to have a solution, and you need more. You need first that the Prand equation, if they have a nice solution, this will describe the solution near the wall. Well, that's not always the case. Even if out of the analytic case, there have been several contributions of Thoan and Grenier, who shows that even if not the analytic case, but in the Sobolev norm, the infinity, for instance, you have a defect between the solution of the Prand and the solution of the Navier-Stokes near the boundary, and which will prevent the convergence. Now, it's also known that the Prand equation may exhibit a singularity after a finite time. So that's reasonable to work only for short time for this problem. And that's okay. Now, of course, if you have, then you can also think about what's happened where in terms of wild solution. We have some case where we can rule out the wild solution in the limit, but that's maybe not in the spirit of what I'm discussing here now. Now, just one last comment I want to make is that what I have done, in some sense, A will be the Navier-Stokes. That in some sense, I have analyzed the Cauchy problem for short time. What's up? You prescribe good initial data, and you say what will happen in the finite time. Well, I want to analyze whatever this type of A may be. This for short time is much simpler than A of U, than considering the equation A of U equal F. For instance, if A is a matrix, this is always a well-posed problem by the Cauchy-Lipschitz theorem, but if 0 is an eigenvalue, you are in trouble. And A of U equal F on some correspond also of what will be the limit when the time goes to infinity, or the relation between how the time goes to infinity between this solution and that introduce either bifurcation, if you look at this problem, or this is the place where you have better to deal with statistical theory of turbulence. Just to conclude, when I made this type of talk in Vienna, in front of people that were really most involved in physics, I had the remark of Zidobert and Procaccia. They told me, Claude, do you think really that if the problem near the wing will be time dependent, the people that sit in the plane, they will be very happy with the plane shaking all the time? Well, that's a reason. But on the other hand, I still think, maybe it's my job, that if I look at the time-dependent problem, it's a first step of the mathematical theory of all the problem. It's a step that may be useful, and I think it's useful to consider. And I say that it may be even, I think that in practical problem, if someone solves the Clay prize, this issue for large time will remain always open for some more time. Thank you for the audience. And these are the picture. Oh, this picture is about boundary layer. That's taken from a book of Uriel Frisch. We took it somewhere. Is explained what is homogeneous isotropic turbulence, which is exactly what you see there. But it omits to say that what is here is a grid, and this is exactly this picture where you have boundary effect which propagate in the media, which is the same in all these pictures, especially in this one, which is numerical computation, where you really see the detachment from the boundary. Okay, that's it.
Thank you very much, Claude. Any questions? I don't see anybody in the audience here. Any questions from our online participants? Okay. So, Claude,
Can I ask a question?
Yes.
Yeah.
Claude, who do we go back? I can't remember the slide, but you got things down to a quadratic inequality.
To which one?
Well, you had a quadratic inequality in
Yes. Yeah. Yes. Oh, I see what your question. I think I can answer.
and you talked about the initial data.
Yeah, I want to show to combine it back to it.
Yeah.
Yeah. Yeah.
Yes, that was it. The other slide. Yes.
Yeah,
So
that's it. You have a function. you have a function which depends on the time, okay?
Yeah.
Then you have a constant, and you have the square of this function with coefficients.
Right. Right.
I call
Now,
this
is
quantity.
this-
I
Is
call
this
this.
coefficient positive? Is the
I call,
coefficient?
yeah. I call this quantity x of t, say.
All right.
And I look at the parabol, which is the right-hand side moving on the other side, which is CA, the constant, plus the coefficient x squared of t minus x of t.
Right.
I start from a region where this parabola is positive. But you know, when it construct like that, there are two roots. One is x1 and the other is x2. There are both roots. When this expression is small enough, these roots are both positive.
Right.
I start from an initial data, which is x, where the initial data, where this quantity is positive, say near 0. I look at how x of t evolves. Since it has to remain in the region where it's positive, it cannot cross x2. Because maybe the simplest way to explain that, but this is a type of thing that appears whenever you have something quadratic and you have a smallness hypothesis on the delta at the time 0, and you want to show that this hypothesis remain true over the time.
Yeah, okay, yeah, that was what I wanted to know. Okay, thank you.
Okay.
If there are no more questions, let's thank Claude one more time. Thank you.